Earlier we discussed how sharp quantities arise as the result of our measurement. Okay. Now let us see how a sharp quantity arises as the result of our calculation. Okay. When does a sharp quantity appears in our calculation? I have written something here, we will look at that. Now we know that an act of measurement is mathematically represented by the action of an operator on a wave function, right? An operator acts on a state which is represented by a wave function. Now some states are special for an operator. Okay, so this is the idea. Some states are special for an operator. They are unique for an operator. What is special there? In general, when an operator acts on a wave function or an operator acts on a state, the state changes. Physically, what we can say is that when we do measurement on a state, the state changes. Remember that when we do measurement on state A, in general state A changes to state B. Mathematically, we can say when an operator corresponding to that physical quantity acts on the wave function corresponding to that state, the wave function changes. But some states are special. How? In what sense? Here, when the operator acts on the wave function doesn't change. Okay, what happens is we get the same wave function multiplied by some scalar. Like this. Say the operator A acts on the wave function psi, we get the same wave function psi, there is no change. And the only change is that the same wave function we get multiplied by some scalar A. Physically, we can say that when we measure this physical quantity corresponding to this operator on the state corresponding to this wave function, okay, there is no change in that state. So this type of a situation is a special situation for an operator. Because in general, when the operator acts on a wave function, it should change. But here it doesn't change. We get the same wave function multiplied by a scalar. Now this scalar, okay, is called eigenvalue of the operator A. And this state psi is called eigenstate of the operator A corresponding to the eigenvalue A. Okay, this is the eigenstate of the operator corresponding to this eigenvalue. When the eigenvalue changes, the eigenstate will change. Now this type of an operator equation, this is called an eigenvalue equation. An eigenvalue equation. This eigenvalue and eigenstate are German words. The meaning is, the meaning of eigenvalue means characteristic value. Characteristic value means unique value, special value. Okay. Similarly, eigenstate means the word mean. This word eigenstate means characteristic or unique state or special state. So this the word eigenvalue and eigenstate simply means special value, special state, characteristic value, characteristic state. So the what is characteristic or unique or special about the state is that the operator acts on the state and we get the same state multiplied by a scalar. Now, what is the connection of this with the sharp quantities? Okay. Now, in our measurement, physical measurement, in the experimental measurement of a physical quantity, we get a sharp value, right? In some cases, we get a sharp value. Now, this sharp value that we obtain as the result of a measurement is nothing but the eigenvalue, one eigenvalue of the operator. Okay, so what is a sharp value? It is one of the eigenvalues of the operator. There is a connection between sharp value and eigenvalue. When do we get a sharp value? We need not get sharp value always. In order to get a sharp quantity as the result of our physical measurement, the system should be in a particular state. Okay, what is that state? That state is nothing but the eigenstate of the corresponding operator. So we can say that this equation, the eigenvalue equation, is the mathematical representation of a measurement where we get a sharp value as the result of our measurement. Okay, this is the sharp value that we get as the result of our measurement, and the state in which we get this sharp value is nothing but this sharp value is the eigenvalue of the operator, and the state where we get sharp value as the result of our measurement, this state is nothing but the eigenstate corresponding to that eigenvalue. Okay, so coming back to our original question, when does a sharp quantity appear in our calculation? Okay, it appears as the eigenvalue of the corresponding operator. So the eigenvalue equation is simply a mathematical representation of the measurement of a sharp quantity. Okay, an eigenstate is a conventional practice is that an eigenstate is labeled in terms of the corresponding eigenvalue. For example, if we go back to our eigenvalue equation, an operator acts on a wave function, we get the same wave function multiplied by a scalar. This is the eigenvalue, this is the eigenstate. And since psi is the eigenstate corresponding to this eigenvalue, psi can be marked like this, psi suffix a. So the eigenstate is labeled in terms of the eigenvalue. Now, sometimes it is possible that the same state can be the eigenstate of more than one operator. For example, okay, there can be the same state. Suppose another operator acts on the same state, and we get the same state multiplied by another scalar. Okay, so this psi and this psi are the same. Okay, let me. So here this can be labeled as psi a. Okay, based on this eigenvalue. Now the same state is the eigenstate of another operator. Another operator acts on the state, we get another eigenvalue. Okay, then it means that psi can be labeled in terms of this eigenvalue as b. So this makes some confusion if we use this symbol and this symbol. So what we do is we combine this and we label the wave state in terms of both a and b. Okay, so this can go on depending upon how many operators are there for which the state is the eigenstate. It's a common eigenstate for how many operators. We can label the state in terms of all those eigenvalues. Okay. Okay, now let us consider our previous example of when we discussed the sharp quantity. We introduced sharp quantity. We considered measurement of energy in the ground state of energy of the hydrogen atom. This ground state of energy of the hydrogen atom, the wave function for the ground state of energy of the hydrogen atom is we write it like this: psi 1 0 0. You notice that there are three labels here. So this necessarily means that there are three operators, okay, whose this state is the eigenstate of three operators. Actually, there are four operators, but conventionally we label the stationary states in hydrogen atom in terms of three of them. Okay, so let us consider. I will come back to this labeling later. So this label is just like this. The state is labeled in terms of three eigenvalues. Okay, so this the value of this state is psi 1 0 0 is 1 by square root of phi a0 cube e raised to minus r by a0. This is the wave function for the ground state of hydrogen atom, where a0 is Bohr radius. Okay. So when we measure energy in the ground state of energy of the hydrogen atom, the results of we did some 10 trials, and every trial gives the same value, minus 13.6 electron volt, right? That was our physical measurement, experimental measurement. Now how do we mathematically represent this? So energy measurement means energy is the operator corresponding to energy is Hamiltonian operator. It acts on this state psi 1 0 0. Okay. Now this state is an eigenstate for the energy operator. So it should satisfy an eigenvalue equation like this. What is the eigenvalue? Eigenvalue of the energy operator is nothing but the corresponding energy value E1. Okay, where E1 is minus 13.6 electron volt. So our physical measurement of energy in the ground state of energy of hydrogen atom is mathematically represented by this eigenvalue equation. The ground state of energy of the hydrogen atom is an eigenstate of energy operator. Therefore, when this energy operator acts on this ground state, we get the energy eigenvalue multiplied by the ground state. Physically, it means that in every trial of energy measurement, okay, we are going to get the same eigenvalue, because this state is the eigenstate of the energy operator. Okay, so in every trial we get the same value, and that is why we call it a sharp value. So the idea is this: a physical quantity is sharp, okay, in its own eigenstate. When the system is in an eigenstate for the operator corresponding to that physical quantity, then every measurement of that physical quantity gives the same value, right? Every trial of measurement of the physical quantity gives the same value. Mathematically, what happens is the state in which we are doing the measurement is an eigenstate, a special state for the corresponding operator, the operator corresponding to the physical quantity. In such a situation, every action of the action of the operator on that state gives a value, eigenvalue corresponding to that state. So every measurement will give you the same eigenvalue. So that's why we say that a physical quantity is sharp when the system is in its own eigenstate corresponding to that operator. Now let us consider these two features of eigenstates and eigenvalues. When the system is in an eigenstate of the operator corresponding to the physical quantity we measure, then first feature is that each trial of the measurement gives the same value. Okay, this we have already seen. This is the eigenvalue of the operator for that eigenstate. And when each trial of the measurement gives the same value, we call that physical quantity a sharp quantity. Okay, so in other words, we can say that a physical quantity is sharp in its own eigenstate. Okay, so this is one feature when the system is in an eigenstate of the physical quantity that we are going to measure. This is one feature. Every trial gives the same value, which is the eigenvalue of the operator for that eigenstate. Or in other words, the physical quantity is sharp. Now the second feature, and also one point is that in this case, we can predict beforehand the result of every trial of the measurement. What is that result? The eigenvalue for that operator. Remember, when the hydrogen atom is in the ground state, we can predict beforehand what is going to be the result of every measurement of energy. The eigenvalue for that ground state of energy, which is 13.6 minus 13.6 electron volt. So we can predict beforehand the result of every single trial of measurement. The second feature is that immediately after the measurement of the physical quantity, the system remains in the same eigenstate. How do we know this? We can check this by making two back-to-back measurements on the same member of the ensemble. Usually what we do is, we know that we have an ensemble. If we want 10 trials, we have an ensemble of 10 systems, and we make a single measurement on each system. Why? Because we know that the state will change. But in order to check whether the state actually changes in this case, we can do 2 or more measurements on the same member of the ensemble. Okay, for example, consider hydrogen atom in the ground state of energy. Consider one member of the ensemble. So we have a single hydrogen atom in the ground state of energy. We make one measurement of energy, we get minus 13.6 electron volt. We make the second measurement on the same member of the ensemble. Okay, immediately after the first measurement. Again we get minus 13.6 electron volt. We do a third measurement, we get minus 13.6 electron volt. So this shows that immediately after the measurement, the system remains in the same eigenstate. In other words, when the measurement of a physical quantity in its own eigenstate does not change the state. Okay. Generally we say that when we measure a physical quantity in state A, the state A changes to state B. But if our state is the eigenstate of this physical quantity or eigenstate of the operator corresponding to this physical quantity, that state does not change. In fact, that is what is meant by the eigenvalue equation. That is what is special about the eigenstate. When the operator acts on the eigenstate, you get the same state. Okay, multiplied by a scalar. The state doesn't change. This is what we observe physically in our experimental measurement. Immediately after the measurement, the system remains in the same eigenstate. This can be experimentally verified. So these are the two features of an eigenstate. If the system is in an eigenstate of the operator corresponding to the physical quantity that we are going to measure, then one is that we can predict beforehand what is going to be the result of every single trial of measurement. That result will be the same. Okay, every single trial gives the same value, which is the eigenvalue of the operator corresponding to that eigenstate, right? And that's why we call this physical quantity sharp. In other words, a physical quantity is sharp in its own eigenstate. And second feature is that immediately after the measurement, the system remains in the same eigenstate. In other words, measurement of a physical quantity in its own eigenstate does not change the state. Let us consider some simple problems on eigenvalues and eigenstates. First problem, let us check, check if e raised to 2x is an eigenstate of the operator d by dx. And if it is an eigenstate, then calculate the eigenvalue. So, what is the condition for a state to be an eigenstate for an operator? This is the condition. An operator acting on the state should give the eigenvalue times the same state. Okay. Now here our operator is d by dx. Our state is e raised to 2x. So what happens when d by dx, a differential operator, acts on this state, this wave function? So what is d by dx of e raised to 2x? Okay, we get 2 times e raised to 2x. Let's compare this equation with this equation. We can see that operator acts on the wave function, we get a scalar times the wave function. So this is an eigenvalue equation. It means that e raised to 2x is an eigenstate of the operator d by dx, and the eigenvalue is 2. Right? Consider another variation of this problem. Consider two wave functions, psi1 equal to e raised to 2x, psi2 equal to e raised to minus 2x, okay, and the operator is d by dx. So let us check these two wave functions, if they are eigenstates of the operator d by dx, and if they are eigenstates, what are the eigenvalues. So we can see that d by dx acting on e raised to 2x is 2 times e raised to 2x. So it's an eigenstate as we have seen in the first problem, and the eigenvalue is 2. Now d by dx acting on the second wave function e raised to minus 2x, we get minus 2 times e raised to minus 2x. This is again an eigenvalue equation of this type. Here the scalar is minus 2, that means eigenvalue is minus 2. So e raised to psi1, that is e raised to 2x, is an eigenstate of this operator corresponding to eigenvalue 2. Psi2 is also an eigenstate of the operator corresponding to another eigenvalue minus 2. So corresponding to the eigenvalue 2 we have an eigenstate, corresponding to the eigenvalue minus 2 we have another eigenstate. Okay, we can see that here corresponding to one eigenvalue there is only one eigenstate, right? This is called, or these eigenstates are called non-degenerate eigenstates. Of d by dx. So psi1 and psi2 are non-degenerate eigenstates of this operator. Why they are called non-degenerate? Because corresponding to one eigenvalue there is only one eigenstate. So are there situations which where this is not so? There are. Okay, let us see one example of such a situation. Let us consider another variation of the second problem. Consider two states, psi1 equals, okay, consider the same two states, e raised to 2x, psi2 e raised to minus 2x, and consider the operator d square by dx square, a second derivative. So as before, as in problem 2, let us check whether these two states are eigenstates of this operator, and if so, what are the eigenvalues. So we can see d square by dx square acting on e raised to 2x. It means that d square by dx square actually second derivative, okay? D by dx acting twice. So what is d square by dx square acting on e raised to x? We know that when d by dx acting on e raised to x is 2 times e raised to x. Again one more derivative, you get another 2 times e raised to x. So what you get is 4 times e raised to 2x. This is again an eigenvalue equation. Operator acting on a state gives some scalar multiplied by the same state, right? And what is the eigenvalue here? 4. Okay, and consider the second state, d square by dx square acting on e raised to minus 2x. So when d square by dx square, so it means d by dx acting twice. So d by dx acting on e raised to minus 2x, we get minus 2 times e raised to minus 2x. Again one more d by dx acting, we get another minus 2 times e raised to minus 2x. Minus 2 into minus 2 will be 4. So we get the eigenvalue equation like this. This shows that e raised to minus 2x is also an eigenstate of this operator d square by dx square corresponding to the eigenvalue 4. Now this situation is different from that in problem 2. Corresponding to the same eigenvalue 4, we have two different eigenstates, e raised to 2x and e raised to minus 2x. Okay. Now this type of a situation where corresponding to one eigenvalue you have more than one eigenstate. This is called degeneracy. Okay, this is called degeneracy. So we can say psi 1 and psi 2 are degenerate eigenstates of the operator d square by dx square. And in this particular example, the degeneracy is twofold. Okay, because corresponding to one eigenvalue, you have two eigenstates. Okay, so this is a twofold degeneracy. We say that psi 1 and psi 2 are twofold degenerate eigenstates of d square by dx square, or they are doubly degenerate eigenstates of this operator. Similarly, there can be three eigenstates corresponding to a single eigenvalue. Then we call it threefold degeneracy, fourfold degeneracy, etc. Okay. Now, as one more problem, let us show that the free particle wave function is an eigenstate of both momentum and Hamiltonian operators. In other words, momentum and energy operators. Hamiltonian is nothing but total energy operator. So let us show that free particle wave function is an eigenstate of both momentum and Hamiltonian or energy operators. Let us see. So what is our free particle wave function? Consider one-dimensional case. So free particle wave function is some constant times e raised to I kx minus omega t. Right? So this represents a wave traveling along the positive x direction. A simple harmonic wave traveling along the positive x direction. That represents a free particle. Now let us consider first momentum operator. Right? So momentum operator, I am dropping the suffix x. It's obvious that we are considering momentum along x direction. So P acting on psi, okay, gives you, what is P actually? Minus IH cross dou by dou x acting on psi. That's equal to minus IH cross times, what is the derivative of this wave function with respect to x? What you get is A is a constant, e raised to I kx minus omega t. Okay. And the coefficient of x should come out. What is the coefficient of x? Ik. So what you get is Ik times A e raised to I kx minus omega t, which is nothing but psi. So what is this product? I into I is I square is minus 1, minus of minus will be plus. So we have h cross k times psi. So what you get is momentum operator acting on psi is h cross k times psi. This is an eigenvalue equation. Okay, so psi, the free particle eigenfunction, is an eigenstate of momentum operator corresponding to the eigenvalue h cross k. Now consider energy operator, Hamiltonian. What is the Hamiltonian operator for a free particle? In general, Hamiltonian is kinetic energy operator plus potential energy operator. But for a free particle, there is no force acting on it. So potential energy is 0. Then there is only kinetic energy operator. So here the Hamiltonian operator is simply kinetic energy operator minus h cross square by 2m dou square by dou x square acting on the wave function psi. So what do you get? Minus h cross square by 2m into second derivative of psi. First derivative of psi with respect to x gives ik times psi. Then you have to do one more derivative with respect to x. So again differentiating psi with respect to x, we get again ik times psi. Okay, so we get ik into ik. So that is ik into ik times psi. So what is this? I into I is I square is minus 1, minus into minus will be plus, k into k is k square. So what you get is h cross square k square by 2m psi. Okay, so Hamiltonian operating on psi is h cross square k square by 2m psi. This is also an eigenvalue equation. Hamiltonian operating on psi is some constant times psi, an eigenvalue equation. So it means that the free particle wave function is an eigenstate of Hamiltonian operator corresponding to the eigenvalue h cross square k square by 2. Okay, so we can say free particle wave function is a common eigenstate, or another word used is simultaneous eigenstate for both momentum operator and energy operator. Okay, so I have mentioned that earlier. I have mentioned that a single eigenstate, a single state can be an eigenstate of more than one operator. Okay, then we can label that state in terms of the eigenvalues of all these operators for which the state is the common eigenstate. In the same way, this free particle state we can label as psi. Okay, in terms of this eigenvalue h cross k and this eigenvalue h cross square k square by 2. So maybe we can write as h cross k, comma h cross square k square by 2. Okay, normally we don't do like this. Normally we use more compact notation, but this is possible. We can label it like this. And remember, coming back to labeling, we can come back to the labeling in the ground state of the hydrogen atom. What was that labeling? Psi 100, right? What is the meaning of this one? Remember that I mentioned earlier in one of the discussions that the ground state of energy of the hydrogen atom, we can have in the ground state of energy of the hydrogen atom or in any stationary state of hydrogen atom, we can have 4 sharp quantities. Okay, what are these 4 sharp quantities? Energy, magnitude of orbital angular momentum, one component of orbital angular momentum, which is normally conventionally taken as z component, one component of spin angular momentum, conventionally taken as again z component. So these 4 quantities are sharp in any stationary state of hydrogen atom. So if we take the ground state of hydrogen atom, we have these 4 sharp quantities. So if these 4 quantities are sharp, it means that this is the eigenstate of 4 different operators. Energy operator, it has its own eigenvalue, that's a one sharp quantity. Angular momentum operator, right, it has its own eigenvalue, another second sharp quantity. Z component of the angular momentum operator, this is total angular momentum operator, this is Z component. So it has its own eigenvalue, and a third sharp quantity. Z component of spin angular momentum operator, it has its own eigenvalue, a fourth sharp quantity. But conventionally, the stationary states of hydrogen atom are labeled in terms of the first 3 quantities, first 3 sharp quantities. So these are this labeling actually is in terms of the first 3 sharp quantities. So what are these values? Energy value. So actually use for this label we are not using the actual physical quantities as I have done here, because it will be a large value. So what we do is these physical quantities are all quantized. So we use their quantum number for labeling. Okay. So the quantum number for energy is called the principal quantum number n. Quantum number for angular momentum is called orbital quantum number L. Quantum number for z component of angular momentum is called magnetic orbital quantum number ML. Similarly, quantum number for z component of spin is called magnetic spin quantum number MS. Now for the ground state, this n is equal to 1. This is corresponding to the energy minus 13.6 electron volt. So instead of labeling in terms of minus 13.6 electron volt, we simply use the quantum number corresponding to that energy, which is n equal to 1. And for the ground state, the quantum number for orbital angular momentum is 0. This corresponds to the angular momentum, magnitude of angular momentum 0. So when we use this 0 here, it is not actually the magnitude of angular momentum, but this orbital quantum number 0, the second one. So this is n and this is L. And the magnetic spin quantum number is 0. This corresponds to the z component of spin angular momentum 0. So instead of using this value, we are actually using this value. So this third 0 corresponds to ML equal to 0. And this one, there are two possibilities here. Okay, MS can be plus or minus half. This corresponds to SZ is equal to plus or minus half H cross. Now this fourth quantity, we don't use it because it has two possibilities. Okay, so in the this can be measured only in the presence of a magnetic field. So in the absence of a magnetic field, we cannot measure it. So normally we label the stationary states of hydrogen atom in terms of these first three sharp quantities, or the more correctly in terms of the quantum numbers corresponding to the first three sharp quantities. So whenever you have a state which is a common eigenstate of more than one physical quantity, then we label it in terms of all the eigenvalues, in terms of the eigenvalues of all these operators for which this state is a common eigenstate. So this is a common eigenstate for 4 operators, and we use the eigenvalues of first three of them to label the state. That is the idea. So coming back to our problem, the free particle wave function is a common eigenstate for momentum as well as energy operator.